Hi, here we are going to see about the Unit 3 continuation. So let me see the one by one. So here there is going to see about the structure of FIR filters. So there is the realization of the FIR filters given by transversal structure, linear phase realization, polyphase realization. So transversal realization is of two types. One is direct form realization and cascade form realization. First we are going to see about the direct form realization. So in this realization, that is the FIR filters can be written as h of z is equal to summation n equal to 0 to n minus 1 h of n z power minus n. So that is equal to h of 0 plus h of 1 z inverse plus h of 2 z power minus 2 plus etc. plus h of n minus 1 z power minus n minus 1. So y of z is equal to h of 0 x of z plus h of 1 z inverse x of z plus h of 2 z in power minus 2 x of z plus etc. plus h of n minus 1 z power minus n minus 1 x of z. So this structure is known as a direct form realization. It requires n multipliers. So n minus 1 adders and n minus 1 delay elements. So that should be drawn in this method, that is x of z, here is the y of z. So first is h of naught into z inverse, then h of 1 into z power minus 2, there is next is h of 2 into x of z into z power minus 2, 3, likewise it will be used up to h of n minus 1. Next we are going to see about the cascade realization. So there is, to determine the direct form realization of the following system function, there is the system function is given, that is h of z is equal to 1 plus 2z inverse plus 6z in power minus 2 plus 4z power minus 3, 5z power minus 4 plus 8z power minus 5. So h of z is equal to y of z by x of z. So there is y of z is 1 plus 2z inverse plus x of x 6z in power minus 2 plus 4z power minus 3 plus 5z power minus 4 plus 8z power minus 5. So that is y of z is equal to x of z into this term. So for this equation y of z, we have to draw the cascaded diagram from realization diagram. So this will be here. Next, obtain the cascade realization of the system function. H of z is equal to 1 plus 2z inverse minus z power minus 2 into 1 plus z inverse minus z power minus 2. So there is h of z is equal to h1 of z into h2 of z. So where h1 of z is 1 plus 2 inverse 2z inverse and h2 of z is 1 plus 2z z inverse z power minus 2. Okay, so there is h1 of z is equal to y of z by x1 of z. So y1 of z is equal to x1 of z into plus 2z inverse x1 of z minus z e to the power minus 2x of z. Next, h2 of z is equal to y2 of z by x2 of z. So that is y2 of z is equal to x2 of z plus z inverse x2 of z minus z power minus 2x of z. So this equation 1 and 2 can be realized in the direct form and can be cascaded as shown in the figure. Next, obtain the linear phase realization of the system function. So h of z is given. So for this we have to find the system function. So h of n is equal to h of n minus 1 minus n. So therefore we can realize the system functions. So there is x of n is given, here is the y of n. So for this we have to draw the realization system. Next, the lattice structure. So the lattice structure formulas are Qm of 0 is equal to 1, Qm of m is equal to Km, Qm of k is equal to Qm minus 1, k plus Qm of m, Qm minus 1 into minus m minus 1. So consider the FIR lattice filter with the coefficients. So K1 is equal to 1 by 2, K2 is equal to 1 by 3, K3 is equal to 1 by 4. So determine the FIR filter for the direct form structure. So the FIR lattice filter with the coefficients are K1 is equal to 1 by 2, K2 is equal to 1 by 3, K3 is equal to 1 by 4. Determine the FIR filter for the direct form structure. So the FAR filter, the FAR lattice filter with the coefficients are K1 is equal to 1 by 2, K2 is equal to 1 by 3, K3 is equal to 1 by 4. So Q3 of 0 is equal to 1, Q3 of 3 is equal to K3 equal to 1 by 4, Q2 of 2 is equal to K2 is equal to 1 by 3, Q2 of 1 is equal to K1 is equal to 1 by 2. So we know that Qm of K is equal to Qm minus 1 of K plus Qm of M, Qm minus 1 into M minus 1. So for M is equal to 2 and K equal to 1, that is Q2 of alpha, Q2 of 1 is equal to Q1 of 1 plus Q2 of 2 into Q1 of 1. So that is 1 by 2 plus 1 by 3 into 1 by 2, that is equal to 2 by 3. For M is equal to 3 and K is equal to, so there is the Q of 1 is equal to Q of 2 of 2, 1 plus Q of 3 of 3 into Q of 2 of 2. So for M is equal to 3 and K equal to 2, we have to substitute the values. So likewise, the lattice filter coefficients are Q3 of 0, Q3 of 1, Q3 of 2, Q3 of 3. We have to find the answers. Next is the design of FAR filters. So the FAR filters can be designed using three following techniques. One is the Fourier series method, second is windowing technique, third is frequency sampling method. The filter design using the window techniques that can be given as the desired frequency response of any digital filter is periodic in frequency that can be expanded in the Fourier series. So ht of e power j omega is equal to summation n equal to minus infinity to infinity ht of n e power minus j omega n, where ht of n is equal to 1 by 2 pi integral minus pi to pi h of e power j omega into e power minus j omega n into d omega. So the Gibbs phenomenon is defined as n is equal to plus or minus m minus 1 by 2. So there are three types of windows. One is rectangular window, Hamming window and Hanning window. So for rectangular window, the formula is WR of n is equal to 1. For m is for modulus of m minus 1 by 2 is less than or equal to n, less than or equal to modulus m minus 1 by 2. Next 0 for otherwise. For Hanning window, it should be written as WH of n, Hn of n is equal to 0.5 plus 0.5 cos 2 pi by m minus 1 for a minus m modulus of m minus 1 by 2 is less than or equal to n less than or equal to modulus of m minus 1 by 2 or 0 for otherwise. Hamming window is defined as, that is WHM of n is equal to 0.54 plus 0.46 cos 2 by m minus 1 for minus of modulus m minus 1 by 2 is less than or equal to n less than or equal to m minus 1 by 2, 0 for otherwise. So if the filter coefficients HD of n for different types of filters, there is a low pass filter means the HD of n is WC by pi for n is equal to alpha, and HD of n is sine omega c into n minus alpha divided by pi into n minus alpha for n is not equal to alpha. So for high pass filter it is 1 minus omega c by pi for n is equal to alpha, and next thing is 1 by pi c into n minus alpha into sine n minus alpha pi minus sine n minus alpha into omega c for n is not equal to alpha. So band pass filter is, for if n is equal to alpha means omega c2 minus omega c1 by pi. If n is not equal to alpha means 1 by pi into n minus alpha into sine omega c2 into n minus alpha minus sine omega c1 into n minus alpha 1. If it is a band stop filter means that is n is equal to alpha means 1 minus omega c2 minus omega c1 by pi. If it is not equal to alpha means 1 by pi into n minus alpha sine omega c1 into n minus alpha minus sine omega c2 into n minus alpha plus sine into n minus alpha into pi. So now we are going to see about the ideal low pass filter with the frequency response problem. So first step is to find the filter coefficients. So there is 1 by 2 pi integral minus pi to pi h of e power j omega by into e power j omega into d omega. So 1 by 2 pi integral, for limit we have to substitute pi by 2 minus pi by 2 to pi by 2. 1 into e power j omega into d omega. So that will be sine into n minus alpha into omega c by pi into n minus alpha. if alpha is equal to 0. So sin pi by 2 n by pi, that is minus 5 less than or equal to n less than or equal to 5.